Okay, X28, the second law of thermodynamics. The second law of thermodynamics, in short, delta S, change in entropy is never negative. Remember, delta S equals 0 process is called reversible, and probability of A to B is the same as the probability of B to A. So reversible process means A and B states is something like equivalent in probability, and they can go forward and backward. It's possible. If delta S is a positive, only this process is allowed and reverse process is disallowed. That means this process is called irreversible process. And delta S negative process doesn't exist in thermodynamics. So dirty mirror does not clean itself spontaneously. That is delta S negative. Process with delta S negative does not occur spontaneously. The reverse process of a process with this does not occur spontaneously. That's the second law of thermodynamics. An example is a rubber band problem. According to the first law of thermodynamics, with the condition, we assume a spring is elongated due to an external force, but keeping the temperature the same. If the temperature of a rubber band is invariant, so isothermal process, then supplied heat is completely used. Supplied heat to the system is completely used by the mechanical energy. The work done by a rubber band can be computed by the scalar product of the force and the displacement. If you elongate a rubber band is a kind of spring, the force applied by this rubber band is opposite to the displacement. Right? Minus kx. Therefore, if you make use of the magnitude and positive definite displacement, we have negative sign on it. It is always the displacement and the force, they are opposite direction. The work done by the rubber band is negative definite. If we require the internal energy of the band, the temperature is the same, then the internal is 0. In that case, the heat transfer to the rubber band is completely used by the work done by the rubber band. And we can make use of the entropy. The entropy change is defined by the heat transfer to the system divided by the temperature. Because the internal energy is invariant, the temperature is well defined as a constant value. We make use of the first law of thermodynamics, dQ. The supplied heat is by definition TdS, should be the sum of change in internal energy and the work done by the system. The system is rubber band, and the work done by the system is minus FdX. Now, from this this one and this one. Fdx is, we exchange the position. So Fdx equals internal and TdS is negative sign. From this, we divide both sides with the differential dx. The force can be computed as the sum of two derivatives. Because the internal energy is assumed to be constant, only the entropy changes. From this, we can determine the change in entropy. The answer is this. And both temperature and magnitude of the force are positive. Change in entropy is negative. We remember the second law of thermodynamics. ds negative or dx is a positive indicates the elongation of the rubber band is decreased entropy. So it usually tends to return to the equilibrium position, original position. That's reasonable. So rubber band tends to restore the original form spontaneously, according to the second law of thermodynamics. So hence we say the rubber band behaves like an entropy spring. Next, we consider Boltzmann's definition of entropy. Here, W is the multiplicity of a system. Why don't we consider a composite thermal system? We have system 1 and system 2. They are in thermal equilibrium at temperature T. And what happens to the case we would like to express the entropy of the total system in terms of the entropies of the two systems? We can count the entropy by making use of Boltzmann's definition, multiplicity of the subsystem S1 and multiplicities of subsystem S2. Because the two systems are independent, except that they are in thermal equilibrium at temperature T, the number of multiplicities in system 1 is W1. Number of multiplicity of system 2 is W2. And when we count the number of cases of a composite system, the multiplicities multiply. Therefore, the product of the two multiplicities constructs the multiplicities, number of multiplicities of the composite system. We take the log of both sides, and log of product is the sum of logs. And we multiply the proportionality constant, Boltzmann constant Kb, then what we find is the entropy of the composite system and sum of entropies of the two systems. So entropy is additive. Entropy is additive because the probability is being multiplied. We can generalize this idea to a composite system of n statistically independent systems. Then again, we take the log of both sides, and this one becomes the composite system's entropy is simply the sum of every partial system's entropies. We recall the Maxwell-Boltzmann distribution for the molecular motion in a gas. And in here, we had exponential factor that is actually the 2kBt over mx vector dot square. Mx vector dot square, that means x vector dot squared means x1 squared, x1 dot squared, x2 dot squared, and x3 dot squared sum. And actually this is 1/2 mv squared, kinetic energy of a single molecule. That kinetic energy of single molecule is divided by kBt. And we put the negative sign on it, and this is the probability of a system of molecules that is in thermal equilibrium at temperature T. So it is less probable as the energy, the kinetic energy of average kinetic energy of a molecule increases. And if it approaches zero, then probability is maximized. However, because of the Jacobian factor from this Cartesian coordinate system to the polar coordinate system, we have a factor of velocity squared. So the maximum does not appear at absolute the zero kinetic energy, instead somewhere around. Remember, exponential function e to the minus x has the maximum value at x equals 0. However, what happens if I have x t e to the minus x, something like that? We have a bump. For example, we have a bump. This is the structure of a Maxwell-Boltzmann distribution. Intrinsically follows the nature of Boltzmann factor, but because of the Jacobian x dot squared, we do not have this monotonically decreasing function, but we have a bump, and this gives the Maxwell-Boltzmann distribution. Next, we consider engine. The engine, this is a PV diagram of an engine. Engine has a cyclic behavior, and we can draw a curve on a PV plane. If we are able to draw a figure as a curve, as a closed curve, that means the engine, the gas of the engine, is in thermal equilibrium at every point. So we can make use of ideal gas equation throughout the whole process. And we remember this area inside the closed curve on the PV diagram represents the work done by the gas. And what is the source of the energy? That is dQ, supplied heat. And what is the output? Output of the engine, that is the mechanical work. What we want to do is to find the efficiency, the supplied heat as an input at high temperature, and the output, that is the work done by the engine. Sure, there is another heat that is coming out of the engine. However, at low temperature, engine loses heat, However, this heat is not used as an output. It is a kind of trash. We are losing this one unavoidably. So even though this is coming out of the engine, but this is a simply byproduct that is not the output of the engine. Because of this existence of unavoidable loss, the efficiency cannot be 100%. In addition, when it returns to the same position, every thermodynamic variable returns to the same value, as well as the temperature. That means the temperature is the same at the same point. That means internal energy is invariant after a single turn, a single cycle. Therefore, if the temperature is the same during a single cycle, delta Q must be the same as delta W. So this is this and this. Out of this, we have by making use of this, we can compute the efficiency. But this dQ, delta Q, is composed of supplied heat and lost heat. Because lost heat is a positive, supplied heat is always greater than the sum of the two heats. That's the point. This is the sum of the two heats. For example, 5 is added. You lost 1. The sum is the net heat supplied to the system. Therefore, the system does work by 4, but the efficiency is 4 over 5. It is always less than 1, something like that. You always lose some amount of energy. That's the key point. Let's go ahead. Because the entropy is the state function that is uniquely defined at every point on the VP plane, the entropy of a gas for engine is invariant after cycle. That's right. PVT and entropy, everything is well defined on the curve. G engine accepts heat transfer at high temperature as an input. It is unavoidable for the engine to lose heat. This amount of heat is lost from the engine at low temperature. This is the fundamental reason why perfect engine is forbidden. Engine performs the work as output of the energy, and the work can be computed as the area inside the closed path on the PV diagram. Heat transfers to low and high temperature respectively. That's what I have explained already. Again, we consider the same plot. The first law of thermodynamics shows the sum of the two heats. This is a positive and this is a negative. So we put the absolute value on it and put the sign explicitly. Then internal energy change and the work done by the gas. That is the first law of thermodynamics. At low temperature, it loses, so supplied heat is negative. Input energy is this one. Not this one, but this one is the input energy. So efficiency is computed as output divided by input. Output is the word. This is input, right? And from this, W, internal energy is the same. So W is QH, absolute value, subtracted by QL, absolute value. So QH minus QL divided by QH. So that's the reason why we have this, and this is always less than 1. It is impossible to have a heat engine have perfect efficiency. So perfect engine doesn't exist at all. Because the entropy S is a state function that is uniquely defined on the PV diagram, delta S over cycle of function return to the same value, then this integral, whatever shape it may have, entropy change should be 0. But at high temperature, it accepts the heat, so this is positive definite, this is a positive definite, so delta S at high temperature should be positive. But because this is negative, we expect that delta S at low temperature should be negative, and the absolute value of these two must be the same to have exact cancellation. Next, we consider Carnot engine. Carnot engine consists of processes, two pairs of processes, TLTH. This means isothermal process, same temperature, constant temperature process. If it is cold, it shrinks. If it is hot, it expands. And the other pair is called adiabatic. Adiabatic process is delta Q equals 0. There is no heat supply. So heat supply and heat loss appears as a constant temperature process, except that adiabatic process. So when you heat it up, at high temperature, its volume expands, and then if it further expands, what happens? Because there is no heat supply to the system, temperature goes down. So it is cooled down. And as soon as it reaches the lowest temperature, the temperature is fixed, and then at low temperature it loses the volume is further shrunk. Okay. Again, it makes a cycle. We are ready to compute everything because we have equipped the ideal gas equation, and we know how to compute the work done by the gas in an isothermal process and in an adiabatic process. Now, we consider the sub-process A to B. At high temperature, the gas accepts the heat. That's right. And in this process, it expands. And temperature is fixed. We can make use of the ideal gas equation and pressure is well known, and it depends only on the volume, and the result is the log of the ratio of the initial final to initial volume. We know VB is greater than VA, so this log is positive. Therefore, the work done by the gas, this process, this area, is log. Sure, NKBTH at temperature, high temperature. Entropy increase because the gas accepts heat at high temperature. At this temperature, entropy calculation is just the delta S, that is a dQ over T at fixed temperature at TH. So we can compute this. This is a positive, so change in entropy at high temperature is just positive, definitely. Next, we consider adiabatic process. Adiabatic process is this one and this one. In an adiabatic process, and actually in the previous class, we evaluated everything in here. So let me just find out the work done by the gas during an adiabatic process can be written in this form. The entropy change can be computed, but in an adiabatic process, without any calculation, we expect that dQ equals 0 always. So even though there is a detailed calculation, we know the answer. Delta S during an adiabatic process must be 0, because this is integral of dQ over T. And there is no heat transfer. Whatever temperature it may have, it is 0. An explicit calculation that we already have evaluated in the previous class in 27. The final result is proportional to the ratio of the initial to final between the two ends of adiabatic process. This ratio we find it is a P times V to the gamma. In an adiabatic process, pressure multiplied by the volume to the gamma is always constant. So that's the reason why we have an exact 0 for the adiabatic process. The two adiabatic process, there is no change in entropy. The only change appears in entropy is in here and here. The heat transfer appears. We continue to consider the process of B2C, and as we have seen, the entropy change is nothing, 0. And the work done by the gas during an adiabatic process is evaluated in X27Q. And the result is this. And this is a positive. It is explicitly this. The work during the A to B is a positive. B to C is also positive. Then C to D and D to A is negative. They are negative. Finally, this area is the work done by the gas during a single cycle. Entropy of G is invariant during an adiabatic process. Very important. The temperature decreases from TH to TL in adiabatic expansion because there is no heat supply, but the gas does work in positive sense. As a result, according to the first law of thermodynamics, the temperature of the gas must decrease from TH to TL. The temperature decreases because the work done by the gas is positive. Yes, right. Then CDA return to the original position. Gas gives away heat during the process C to D. During an adiabatic process, no heat transfer. The G shrinks from CD VC to VD, and temperature is fixed to TL, so it is an isothermal process. The complete amount of energy gained due to the negative work done by gas is transferred to the heat reservoir. Why? It is isothermal process. Isothermal process. There should be no change in the internal energy during an isothermal process. The work done by the engine during the compression period, the C to D is negative, right? It is backward, is negative. Entropy decreases during the process C to D. Sure, entropy increases during this process and entropy decreases during this process. Entropy is invariant during these two processes, and then it returns to the same position after a cycle. The total net entropy change must be 0. So entropy increase during this process must be the same as entropy decrease during this process. So at low temperature, entropy decreases. Adiabatic compression, D to A, heats up. Adiabatic compression, because there is no heat supply and the work done by the gas is negative. Therefore, internal energy must increase and the temperature increases. This is the temperature entropy diagram. You have to distinguish temperature entropy diagram with the PV diagram. Carnot engine consists of 4 subprocesses. 2 subprocesses are constant temperature, and the other 2 subprocesses are adiabatic process. In constant temperature process, temperature is fixed. And during this hot process, at high temperature, entropy increases. And then at low temperature, entropy decreases. You can see the entropy increases, decreases. Finally, it returns to the same value. Entropy is delta S during a whole cycle is 0. Again, we can look into the entropy change in the 2 adiabatic process. Adiabatic process does not involve the heat transfer because the heat transfer is always throughout the adiabatic process. Entropy is fixed. Okay. Heat can be computed. Heat, because the dx is the dq over T, dq equals TdS. Therefore, TdS is identical to dq, and over a cycle, TdS, this is T, this is S, so area, this area represents the heat transfer to the system. The heat transfer to the system is the area, and that area is a sum of QH and QL, and QH is positive, QL is negative. So Using this, the work done by the system means the engine, is QH subtracted by QL, and that is the area of this diagram. Again, we can compute the change in entropy. This change in entropies at high temperature increases, low temperature decreases, but we know after a cycle, it should be zero. This very strong requirement shows that the ratio of magnitude of the heat at high temperature supplied by the environment and the lost energy, magnitude of the lost energy at low temperature, this ratio is identical to the ratio of the two absolute temperatures. Therefore, efficiency of Carnot engine can be computed by the output divided by input, and conservation of energy, that is the first law of thermodynamics, shows that supplied heat subtracted by lost heat, that gives this formula. And constraint of the entropy change must be zero gives great simplification of the heat in terms of the temperature. As far as the heat is concerned, we have to compute the heat. However, temperature is well known at high temperature, low temperature. This formula is simpler than this expression. As a TH goes to infinity, it approaches the efficiency of the Carnot engine becomes 100%. However, making the hot temperature to infinity is practically impossible, and that requires a lot of energy. So, 13. A simpler system, we have a very simple structure in it. Constant volume process instead of in a Carnot engine, we had a very complicated situation appears due to the adiabatic process. Adiabatic process brings in a very strange parameter, gamma, Cp over Cv, and that makes the computation complicated. Instead of using this one, Stirling engine uses a very simple structure that a volume is fixed instead of adiabatic process, except that the other two processes are at the same temperature, that is isothermal process. They say Stirling engine is very calm, so it is used in submarine. Heat transfer to the system. The constant volume process is called Isochoric Process, with dA and BC, constant volume process. During the constant volume process in PV diagram, we know there is no work. Delta V equals 0, so delta W is 0. So during these two processes, the gas does not work at all. The work done by the gas can be simply computed by this area subtracted by this area. So this is the work done by the gas. So work done by the gas can be computed by making use of the constant temperature process. At constant temperature process, we have log of the ratio volume. In addition, this one, they are exactly the same because VA, VB, VA, VB, VB, VA. except that this overall factor that is determined by the temperature, they are different. This is identical. Temperature is different. Therefore, the net work done by the gas is a very simply computable ratio of the volume, log, and temperature difference. Okay. dA, AB. dA, AB. This is high to low temperature, at fixed volume, low to high temperature at fixed volume. Therefore, it accepts heat. And because it is a fixed volume, we can make use of the heat capacity at constant volume. So Q, accepted heat, is this one, from low temperature to high temperature multiplied by heat capacity at constant volume. High temperature to low temperature with the heat capacity. Okay. So total input heat energy is the sum of positive energy transfer to the gas, and that is evaluated like that. Finally, we compute the efficiency of the Stirling engine. So output work divided by input heat. And input heat is just this one, and this is up to here, they are identical to each other. So after applying some algebra, we finally find the efficiency, of the Stirling engine. It looks a little bit awkward in comparison with that of the Carnot engine, but as VB over VA goes to infinity, they approach together. Okay.